Hello my dear students, I am B S Pandey, your physics lecturer. Today we are in lecture number 69 of standard 12th. My dear students, we are studying electromagnetic induction chapter. Okay, so let's start today's lecture. This lecture number 69 of chapter 6 NCERT. It is electromagnetic induction. That is the one of most important chapter which will help in AC. My dear students, what we have studied till now in this chapter actually, and we are continuing with the inductor. In last class we have studied. Okay, this was the inductor. What is the shape of this inductor actually? It is like a spring. You can say the solenoid also. Solenoid can be treated as the inductor, and current flows through this inductor, and this inductor induces an EMF due to change in flux in itself. Okay, if this current is flowing, of course there will be the magnetic field, and due to that magnetic field lines linked with this inductor of flux linked with it. If the flux is constant and this current reaches to the steady value, then it's good. Inductor has no any problem. But we have studied, my dear student, as this current will fluctuate, it will change, then there will be the change in magnetic field and flux. And this inductor having the problem, it will oppose that change in flux which is happening in that conductor, that is the inductor. Sorry. Alright, we have studied there will be a back EMF induced in this inductor to oppose the change which is happening in that inductor. Okay, we have studied if this current is increasing in this direction, then EMF will induce E is equals to L di by dt, and this di by dt, my dear student, actually represented with negative sign which show the direction. Okay, direction of induced EMF with respect to the change in current, in which direction it is changing, increasing or decreasing. If current is increasing in this direction, then the EMF will induce in this direction. Okay, that is, you can consider a battery here behalf of this inductor, and which is in this direction. Why? Because this induces an back EMF. This is the back EMF in this direction. This is the E induced at the back EMF. Okay, my dear students. Now, if we are having the inductor and current is decreasing in this direction, okay, the current is decreasing. Again, we will have the equation. It is E minus L di by dt. We have studied. Okay, but now in this direction the current is decreasing, so the back EMF will support to this current, but it is decreasing. That's why you can consider here a battery, that is the induced EMF. Sorry, the positive will be this side and negative will be to this side. Additional battery you can consider behalf of this inductor. This inductor, you know, that device used to store the energy in presence of magnetic field. What we have studied about this L, my dear student, this was considered as a coefficient of self-induction. Okay, and SI unit, I hope that we have discussed. If not, then we remember the SI unit. It is Henry. In capital, we used to represent with the capital letter H. It is the Henry. Okay, my dear students. Today's lecture we will continue, and we will try to accelerate our topic with the self-induction. We will try to find out the self-induction of various coil. first we have to study that. We have to study in NCERT. We will discuss it is the self-inductance of solenoid, and then we will solve few more questions for the self-inductance of different coil. Okay, so let me solve here so these are the basic concept, my dear students. On the basis of this one, if we will start today the RC circuit under DC supply, then we will study this concept in very detail and we'll solve few numerical question. Okay, yes. Yeah. Okay. So here you can give the heading self-inductance of solenoid. I hope, my dear students, it is not required to explain about the solenoid that we have studied already. Okay. So we are going to find here the self-inductance of that solenoid. Look at here. This is a solenoid. The turnings are given. Suppose the current, it is I flowing through this solenoid of length L, cross-section area A, number of turnings, it is N, number of turns, small n in solenoid we have studied, it was the number density of turning, that is the number of turns per unit length of the solenoid. This I current is flowing. Of course, my dear students, what will happen? There will be flux linked with the solenoid. As this current will change, remember, as this current will change, of course there will be change in flux, and due to change in flux there will be EMF induced, that is the back EMF induced can be considered. But we are going to find here the self-inductance of this particular coil. What we have studied? We have studied the flux, magnetic flux through this particular solenoid will change due to change in current. Okay, and it was phi is directly proportional to I. Okay, this is the I. This is the I. Now, if there is a number of turning n turns, for n turns, we can write this n phi is directly proportional to I, and then we got is equals to L I. Okay, we have to find the value of this L. How we have to proceed? Look at here carefully. My dear students, this is very simple. We are going to proceed from the left hand side, and it is the n phi. Here we have to find L, so the L can be written as n phi over I. Not very tough. Yes, n phi is equal divided by I can be written as this is the L. Now, and it is the number of turning. Alright, you can write this n as n into L also. Remember, this can be also written the n into L. Okay. Now, phi is the magnetic field times area of the solenoid. This is the area of the solenoid, and divided by current. Now, what is the magnetic field associated with the solenoid? We have studied, try to recall. It was the magnetic field due to solenoid, it was mu naught Ni. I hope you remember. And this is the magnetic field due to solenoid. If you are not remember, try to recall. We can put the value of this B over here. Okay, and this will be NL. B, it is mu naught Ni times A divided by I. I will be cancel out, so we will have the equation mu naught N square, okay, A times L. This is the N square mu naught A times, and this is L, and this I will be cancel out. Okay. Now this L is the self-inductance of solenoid. To find the self-inductance of solenoid, we need cross-section area, length, number density of turning, and the permeability of the medium. If there will be some medium inside the solenoid, then again we can find out the self-inductance. This mu naught will be replaced by the relative permeability. Okay, we will discuss in very detail later on. Now, my dear students, this L, which is mu naught N square A into L, the very important question I am going to deal here. In board, sometime it has been asked that compare the energy stored in capacitor, energy density in capacitor, and energy density of solenoid, and also correlate the analog within these two. So to solve that question, we need to find the energy and energy density. But here let me rub this one. Now student, I hope that you can solve any question if you have been asked to find the self-inductance. Remember, to find the self-inductance, what you have to find actually? The flux, basically. Dividing the flux with the current. If there is only one turn, then alright, you will write phi by I. If there are more than one turn, that is the n turns, then you will write n phi divided by I. And the rest are very simple calculations. Okay. Now look at here. Write down a question. Calculate self-inductance of circular coil. Give the heading, calculate self, or derive mathematical expression for self-inductance of circular coil. Self-inductance of circular coil. This is the condition I am giving you. Try to find out. This is a coil of radius R through which current is flowing I. Okay, this is the center from which we have considered radius. You have to find self-inductance of this coil. The singleton, what will be the self-inductance? You have to find. If you can find, pause the video and try to find out the self-inductance of this coil. Let me solve. Here we have to find the self-inductance of this circular coil. My dear students, we know that the phi is equals to L into I. Okay, so to find L, it is phi by I. Who is making the flux? So the magnetic field, it is by this own coil and trapped within this area. So we can write here the B dot A divided by I. B, it is magnetic field due to circular coil. Do you remember? Yes, it is mu naught I divided by 2R. Okay, and divide A, I think with the area, it is A. This is the L. So L will be A, I will be cancel out. So the mu naught pi R square divided by 2R, and it is mu naught pi and R by 2. This is the self-inductance of circular coil. Now, I hope you can solve any questions, so I am giving you a homework. Find self-inductance of given coil. Here I am giving you a coil. You have to find self-inductance of this coil. This is a square coil through which current is flowing I, and the side of this coil is A. This is the square coil of side A. You have to find self-inductance of this coil. Okay, my dear students? Yes. So you have to find this. Now, my dear students, we are going to find here the energy density. As we know that, look at here. If this is inductor, and we know that the current is moving. Okay, if this current is increasing, what happens? The flux that is linked with this coil, there must be some flux like this way. Okay, yes. As this current will increase, what will happen? There will be EMF induced in this direction. This is the back EMF. So the current has to do some work against the EMF. To increase the current, now this current has to do some work against this EMF, because this is the back EMF. Alright? We know that current moves in the direction of the EMF that we consider. If current is increasing in this direction, then this will be considered as a cell, and due to this cell the current will be in this direction. Okay, it means this current has to do some work against this current to increase itself, and this amount of work done which is stored in this inductor, it is called the magnetic energy or the potential energy. But here the potential energy we are considering in presence of magnetic field. So that's why this inductor actually is a device we used to study as a device which used to store the energy in presence of magnetic field, and the amount of work done will be calculated as the potential energy that we are going to consider. We are going to find here the mathematical derivation we will get for the energy, and the very interesting will be that we will compare that energy density with the energy density of capacitor. Okay, so look at here. This is the inductor through which current is increasing, and this is the magnetic flux. Against this magnetic flux, the current has to do, against that back EMF, the current has to do some work, and that work is considered as how much work it will do. Actually, it is Q into E induce. Q into E induce. This will be the E induce. How much charge delivered by this current actually over this particular potential induced by the inductor, that only will be considered as the work. Okay, we don't have to take the potential of the particular section of any different section, but we have to find the work over this inductor. That's why we are considering the EMF over this inductor, and that induced EMF, that is the back EMF. Okay, we know very well. But here the small amount of work done, dW, can be written as the E induced times dq. We can write. Okay, now we know that this current can be written as, my dear students, this current is nothing but the rate change of the charge, that is dq by dt. So that dq can be written as I into dt. This is the very simple explanation, very simple derivation, my dear students. Now we can put the value of dq over here, and it becomes dw is equals to E induced into I dt. Okay, now E induced, which is the back EMF, And what we have studied, the back EMF due to inductor, it is minus L di by dt. Remember, this negative sign only explain you, the negative sign only explain you the sign, that is the direction in which the EMF is induced. Here, L di by dt times I dt we can write, it will be the cancel out. So we will have L I di, and this is the work. Now we'll integrate it from where that we will have the integration. Current starting from 0, there will be no work done, and the current reaches to its maximum value I. So the current, this maximum value I, it will reach, that is steady, and the energy it will be stored, it is as U. Okay, so we can write here with a simple derivation, dW it is as U is equals to L, and I di will be the I square by 2, and this is the energy, half Li square, half Li square. Remember, this L is something in static, the property of this inductor, you can say, which try to maintain its state of rest even due to the change in motion of which charge. Try to recall a quantity that you have been studied from your standard 9th, a quantity that tried to maintain the state of any mass, and that was considered as the inertia. In similar way, here this inductance is working like inertia, electrical inertia, and this electrical inertia actually tried to maintain the flow of, and that is the state of current. If current is in a static state, then okay. Otherwise, if this current is changing, that inertia will oppose that change in current, and due to that inertia an EMF induces. Due to that inertia, there are number of factors induces, the friction you can say. Okay, my dear students, if we will use this negative sign over here, then you will get the negative sign of energy, and this energy actually convert in form of electromagnetic wave. So this inductor is also used to produce the electromagnetic waves. Okay, so try to remember, and this is a very simple derivation, my dear students. U, it is half Li square. Okay, try to remember, this is U half Li square. Now we will try to study here the energy density. Okay, energy density. As we know that energy density, actually give here the heading, energy density okay, and the energy density, it is U defined as the energy per unit volume. Energy per unit volume. Here, what will be the volume? So look at carefully. If this is the inductor, we are talking of the length L and some cross-sectional area A, then volume will be how much? A times L. Okay, this will be the volume of the inductor. The current are moving this, that, okay, the flux is being linked. Now, how much energy we have considered here? The energy, it was half L I square per unit volume, that is A times L. Now U, it is half. L we have considered, now my dear students, do you remember the value of L? We have calculated, it is mu naught N square times volume, that is the AL, and this is the current I square divided by A times L. Now we are going to convert this current in terms of magnetic field produced due to current, that is the change in current, and we know that, here we can write, as we know that for solenoid, because this is the structure of solenoid, the magnetic field, it is mu naught Ni, we can write, and this I can be written as B over mu naught N. Try to put the value of I over here. Okay, this AL will be cancel out, so this will be 1 by 2 mu naught N square, and this I square will be B square over mu naught square N square. I hope you understand. Now cancel out some quantities, like N square will be cancel out by N square, then and mu naught will be cancel out by mu naught. So you will having the equation at the energy density. Remember, this is the energy density. You can change the symbol of energy density as well. This is the U, right? This one, because we have represented the energy also with the U, so this is the small u. So the energy density, my dear students, we can write here the B square over 2, here the N square we consider 2 mu naught. This is the energy density of inductor. Okay, now we are going to compare this with the quantity, but it is quite clear the energy density, it is directly proportional to the B square. Here the magnetic energy, the directly proportional to the square of the field. Now try to compare with the electrostatic energy density. In capacitor, we have written the energy of capacitor. What was it? The energy density, it was half epsilon naught E square. Here the energy density was directly proportional to the square of the field, and this is the correlation between the energy density in presence of electric field in capacitor and energy density in presence of magnetic field in inductor. This is the correlation, you can say. Okay, then after it was correlated, the permeability and permittivity also. Actually, the study of this particular correlation was given by Einstein in relativistic theory to measure the speed and to find the speed of electromagnetic wave. Okay, so this is the energy density, and this type of question will be asked in board. My dear students, so we have discussed today the very simple topics. I will not teach you in so much hurry so that you will not get anything, but these are the simple topic. Next day, my dear students, we will start the combination of this inductor. What will happen here, the inductance of one inductor, it is L. If we will connect two inductor in series, we will connect two inductor in parallel, then what will be the equivalent inductance of that combination of that system? We will study in next class. Okay, my dear student. So this is all about today's lecture number 69. Thank you very much.